Good evening and welcome everybody. This is Obi-Wan Pez for N-Simplex Pachinko, and we are doing some differential equations tonight. We have on the line Ian Stucky with us. If you'd like to introduce yourself.
Sure. I'm Ian Stucky. I'm the host of the Mathematical Creature over on ianstucky.twitch.tv, as well as the I haven't given myself a title for it yet, but the originator of No Royal Road, a geometry study project.
Awesome. All right. So for tonight, hey Phobos. Definitely no worries. So for tonight we have some of our material is going to be taken out of Differential Equations, Dynamical Systems, and an Introduction to Chaos by Hirsch, Smale, and Devaney, which I have here. I am not recommending anybody go buy it or anything, but if you have a particular interest in differential equations, I have found it actually accessible, whereas some of the other books that I have, for instance, the ones that I have been gifted by the retired professor's son, are just absolutely impenetrable. And that's for stuff I studied. It happens sometimes.
Sure does.
Okay, so I wanted to first look at a nonlinear system where we were looking at, and this is going to be a slightly standalone section, which I understand is probably not my best option. But this is the material with which I am probably the least familiar, and I did not actually teach this as part of my ordinary differential equations class, and this is kind of like a bonus topic. And again, it's been 15-ish years since I've even talked about this, so we've yeah, it's been a while, so we'll see how it goes, but
All right. Well, I haven't seen the title of the stream, so I'm going to be surprised.
So nonlinear systems and leading into second-order differential equations. So the first part that we want to talk about is going to be our typical x prime is equal to as a real system, so x is going to belong to an n-dimensional real system of differential equations. Our x is going to belong to a n by n set of matrices, which are going to be our the basis of our differential equations. Generally speaking, this is going to be listed as a function of that particular matrix X. And the other thing that I'm not 100% familiar with is the notation, but I suspect that actually several of my guests might be a little, slightly more familiar with it. Especially if Penn was here. So the function f is assumed to be C1, which I have explained on a slightly previous page here. Anytime if you know what it is, Stucky, feel free and jump in. But
All right. See what we can do.
there we go. C1 is continuously differentiable. And in this particular case, we're just saying that it is once differentiable at least. So it could very well be k times differentiable, but we don't have that information. All it requires is that it is once differentiable. What's really awesome is when you flip the page and then it closes on you.
Oh no.
That's okay. Okay, so for this particular system, we're going to have a matrix big X of t, which is, oops. Is going to be the solution for this differential equation. So another word that I often use with this is just going to be like our actual solution. Because in some cases we are looking at approximations, in other cases we're looking at like the homogeneous solution. This is just the actual solution, so it contains all of the parts that it needs to, everything that we've discussed in previous sections. And we're going to say we're going to let A of t, which is now going to be our transformation matrix as a function of time as we go through this, be equal to our diagonalized matrix. So if we remember from before, this had, was it the eigenvalues along the diagonal and zeros elsewhere?
Something like that. Maybe e to the eigenvalues.
Fair enough, right. And maybe e to that. Which this combined together forms the Jacobian. Of the function f at the point x of t, which is in our real space with n dimensions. All right, this is pretty dense. How are we doing so far?
Not too bad.
Okay. Anything you want to discuss with this one? Any of these definitions so far?
Sorry. F is why is F with the subscripts not the Jacobian?
So F is just going to be our derivative matrix, so it's like all of the bits combined.
Right.
When we had our previous system, that would have been called AX. So our A transformation matrix times our X variable matrix. So F is basically at this point all-encompassing. In previous terms then, right, in stuff that we learned from last time, this would have been diagonalized times A times X.
Okay.
Which our diagonalized matrix had bits that also had inverses in it.
Okay, I'm gonna see if I can't pull up the one from last time. And
yep, I'm trying to pull up my notes from earlier
try
too.
to match some notation. Stream then. Okay, so the mouse wheel or spacebar. Ah, no, there's a zoom. Ooh, I don't think it's saved. I think we, yeah, because of the size of the thing. So you probably have the screenshots already, but,
What was it? The board itself?
Yeah, the board itself.
Okay. Sorry. Remind myself for next time. But it should also be in the elements DE forum. Allegedly.
The variation of parameters is the most recent one that I see.
Uh-oh. Did I not? I may not have hit send on this. I did not. Cool.
See, I thought this was an intentional strategy that you were delaying the posts until the following week. But,
no.
Okay.
No. I meant to do the ones that were at least for those classes immediately.
Gotcha.
Alright, there's that one.
Okay. Seeing it. Beautiful.
Oh, and they're in order. Great.
That is.
Yeah, I had a problem where if I selected them, it would put them in like reverse order, but then if I click drag them from a different window, it put them in proper order. So I don't know what to make of that, but
bizarre. Okay.
That's a problem for another day.
All right, so this A from our previous notation was this derivative of the F matrix at our particular point, which, yeah, is what you were describing. But yeah, I'm still not quite seeing it, but
it's alright, it's probably... I've got one of them in the... it was the week before that, or the time before that, so 8.12. Non-homogeneous systems and general solutions. Let's see, second to last one, I think.
Second to last one. Okay. So eigenvector matrix. Okay, so we are diagonalizing like we're localizing and then diagonalizing. Is that the point here?
That one is attempting to diagonalize so that we just get the eigenvalues on the diagonal. So that was T inverse AT. I believe that this A is probably the updated A rather than...
Right.
So this was the risk for today. So we had T inverse our original A.
I guess maybe I want to see what you have planned for like the next 1 or 2 steps, because
Yeah.
right now I'm happy to just say like, okay, I'm letting this thing exist, whatever it may be.
Let's see. Just see if I can get this real quick to look at this one. If we do that, diagonalize. Need to be T inverse AT. Sometimes that'd be D. This would be like our other one that we did before. Okay, yeah. I probably don't want to go there yet. Okay. So all right, so we're looking at so we got a Jacobian matrix of f at the point x of t in our real space. Then we're saying that this is going to be a continuous family of n by n matrices. It's not necessarily going to be uniquely defined. And this is going to lead us to a possible, so this is non-autonomous. The word autonomous itself just means that our differential equation has no independent variable. In its terms. In maybe other terms that we've heard before, I would probably say it was time invariant. So one example of this would be Newton's law of cooling. If we just take an object out of the freezer and put it on a countertop in our kitchen, and our kitchen remains at a relatively stable temperature forever, then the process of taking something out of the freezer and watching it melt is time invariant. It doesn't matter when this actually occurs. The process is the same. So, whereas in a true, kitchen that's going to be potentially affected by like sunlight, what time of day, like when you're cooking, the temperature is going to be higher. When there's sunlight coming in, the temperature is going to be higher. Middle of the night, it's going to be cooler. If we ignore all those factors or try to normalize for them and then block out all of the sunlight and do all this other stuff, then we would be able to create a time invariant system. In this particular case, this is going to be non-autonomous. So A, our transformation function, does depend on t in some way, shape, or form. Therefore, the system that we have here, u prime equals a of t times u, is going to be non-autonomous. Okay, so what we're going to do here is we're going to define one more function, which this is great because we've got a whole bunch of functions in here already. So we're going to define the function y of t, which is the solution to the autonomous approximation. Of x of t. So provided that u of 0 is going to be provided that u of 0 is sufficiently small, then we're going to have y of t equaling x of t plus u of t. As a reasonable approximation. So this goes fairly similarly to how we did things last class, where basically we're saying that y is essentially like our linearized system from last class. The only difference here is that we're not talking about linearization so much as this time we want y of t to be autonomous, so time invariant, whereas x and u can very well be time variant, I suppose. So u of t is going to be called the variational equation. And so in a lot of differential equations, what we're going to see, or nonlinear differential equations, is that there's going to be a time invariant approximation that we want, y, and then we're going to have this variational equation u, and there are some methods that you can use to figure out simplified systems to end up with solutions which are, again, reasonably approximate as long as you're within a certain area of that particular initial value. This is no longer going to be restricted to our critical points like we did in linear systems, or linearizing the nonlinear systems. Okay, thoughts?
What is the autonomous approximation of xt?
So we don't know ahead of time, but y of t is just going to be something, some system that is going to be a time invariant approximation of our correct solution. We don't know what it is. Obviously, x of t is just going to be like its own. X of t is going to be its own thing. We're kind of deciding a priori that like these things exist.
Okay.
And then trying to figure out if there's a reasonable way to get something that is at least close to the correct answer, and then say either, one, this is going to be good enough, or two, it's going to inform our choices in order to find the true solution.
Okay.
You could say you hate it, that's fine.
A little bit. So I think what I'm supposed to be seeing here is that, like, if I take, am I supposed to think about like f of y, right? And this is supposed to be some approximation to y prime. And that works because you say, well, f at small scales is going to be, f of x is going to be like approximately linear, right? In the sense that you can break apart f of y into f of x plus f of u.
So in this particular case, it's actually not linearity that we care about. So last time it was linearity that we care about. This time it's time variance.
So I care about linearity because if I'm trying to take f of y, because I want to be able to take that, because I want to have f of x, right? And I don't want to have to worry about this extra term here.
Mm-hmm.
But do I want to take f of y? Is that an approximation? Like, is that the...
So in this case, not actually. I don't have
Okay.
f of y anywhere in the book.
Okay.
But what does happen, so throughout this whole process here, okay, so given the system that we have, given that x of t is a solution, u of t is going to be the solution to the variational equation above, u prime equals a times u. Given that they also have an initial point at t0 of x sub 0, u sub 0.
Okay.
And given the fact that y of t is defined to be the solution of x prime equals f of x.
What? Sorry, say that one more time.
Yep, y of t is the solution of x prime equals f of x. That satisfies the initial condition. So I can write this.
Sure. Okay, so y of 0 is x of 0, or no, not x of 0, f of u sub 0?
Yes.
Okay. Okay. Plus x sub 0?
X sub 0 plus u sub 0 is going to be equal to y at t sub 0.
Sure, yeah, t 0. Fair. Okay.
Or y sub 0 if you want to define it that way too.
Sure. Okay. So y prime is equal to, in particular, y prime has to be equal to f of y, right? Or perhaps approximately equal to. And we know that y prime is x prime plus u prime, which is f of x plus a times u, and a is this Jacobian. Okay. Something, some approximation of this Jacobian. Times u. Okay, so this is some. So this approximation here is some like adult version of like a linear approximation for a derivative, right?
I would say so, yes.
Okay. Okay. And so the dream is that we can produce a y that is autonomous while keeping u small. That's the point?
Yes.
Love it. Okay.
Okay. So u prime equals a of t times u, which is our variational equation. Along x of t. For u at t0 equals u0, and 3 y of t is the solution of f, nope, x prime is equal to f of x t0 equals x0 plus u0. Okay, so all of that, if all of that is true, then the following limit.
Okay. I had some stuff backwards, but sure.
The distance between y of t and x of t plus u of t over absolute value of u sub 0 is going to converge to 0 uniformly on t belonging to alpha beta. All right, so maybe let's discuss.
Okay.
Because I have been looking at this all day, trying to 100% parse it, and like I'm probably about 80% the way there.
Yeah. So I'm willing to hold my skepticism, but right now I don't. This doesn't feel non-autonomous to me. Like it feels like the approximation that we're performing here is we're saying, okay, I know some solution, and I want to understand how nearby solutions look. And so, and that's that somehow the conclusion is supposed to tell us something about this. But so yt is approximately equal to x plus u is the point of that limit. Okay, but then okay, I'm keeping this. So yt, the thing I guess I'm nervous about. Oh no, yt is a real solution, but it's a real solution to an autonomous system.
Yes.
So, okay, great. But then x also is. So now I am.
So x is the true solution, which is going to be likely non-autonomous.
But x is a solution to an autonomous system.
Did it say that? And I'm just... Did I literally write that? Sorry, x is the solution to the non-autonomous system.
Okay, so there's like a t dependence in here.
Right. So x is going to be assumed to be the true solution for any ridiculous differential equation we want to come up with.
Sure.
And y is then going to be the solution to the autonomous system that will at least approximate the true differential equation on a local scale. So again,
Okay.
Similarly to how we looked at it in terms of linearity last class, it was that we said, okay, well, we're going to just assume that this is a locally linear system about this particular nodal point. So our critical point that we have here, we're going to assume it's a linear system and then see the behaviors of the stuff that's going to exist around it. And then as we start moving away from it, that's when we start having interactions with the other behaviors. And so that becomes more entangled. Sure. This one is, again, we're looking at it in terms of, okay, the system could be linear or nonlinear. The true differential equation solution, the true system, is probably going to be nonlinear. It could be literally anything. And the true solution is x. But then we're going to say, okay, y is going to be a time invariant differential solution to that particular system, or to that particular differential equation. So in the case of like Newton's method, it would just be some exponential decay function for all temperatures above ambient, and an exponential, well, I guess it's technically still exponential decay, but upward until for all temperatures below ambient. And it doesn't matter where we put that. So if our starting point is somewhere in the past, it's going to be the same curve. It's just going to be shifted left or right, depending on time.
Sure.
So in this particular case, we're saying, okay, the same thing's going to happen here. It doesn't actually matter where we put y It's going to be the same shape no matter where. But we're centering it at t sub 0, x sub 0, u sub 0.
Okay, so I guess that all sounds good to me. I think my question remains is, so in the consider we have an f. In 3 we have an f. These are different because the f in the consider is non-autonomous and the f in 3 is autonomous. Are we being intentionally agnostic right now about the relationship between these two functions?
So I don't think that f by itself is going to drive whether or not this is autonomous. I think that the x and the y are by themselves going to tell us whether or not it's going to remain autonomous. So our function f is not going to impart a t by itself.
Okay.
So again, if like y of t is just an exponential function, then x prime equals f of x. If we plug in y to become y prime equals f of y, then that should not impart a like new t to show up and say t is important and you must use it. It's the nature of x and the nature of y themselves, which are keeping keeping its autonomous status.
Okay, so this is just gonna be a change in thinking, because when I say the word autonomous, I'm trying to be talking about a differential equation, but we're talking about like autonomous or non-autonomous solutions. So this time invariance is really the thing that I have to keep in mind here.
Yes.
I can do that.
Okay.
Okay.
Alright, so there's a lower part saying that our limit as u sub 0 ends up going to 0, so our variation off of our true answer is diminishing further and further. Then this whole fraction here is going to go to 0. Which I think makes sense because of the fact that we have something that is, if u is going to 0, then that means that y and x are going to continually move closer to each other as well.
Yeah, I vibe with that.
Alright, so they also go through a little bit of a blurb here that basically says, so basically this means we have an epsilon and delta, wherein...
Right, of course.
Has to be introduced every time, right? So our distance between y of t and x of t plus u of t is going to end up being less than or equal to, divided by absolute value of u sub 0 is going to end up being less than our epsilon. So we can always pick some sort of like successively smaller u sub 0, which is then going to cause us to be, no, sorry, other way around. we can always pick some sort of acceptable epsilon distance apart that we want these two solutions, or the autonomous solution y away from our non-autonomous x, and then find some delta such that where is it? We can have u sub 0 being less than or equal to delta. Let's move that again. Then we're going to have the distance between our y and the other stuff less than or equal to epsilon times absolute value of u0. And that's going to work for all t within the acceptable interval. So as u0 goes to 0 in its size, regardless of whether it's positive or negative, x of t plus u of t is a better approximation of y of t.
Yeah.
This also uses a system which then I'm not particularly seeing where they're getting their solutions from, unfortunately. And there are no other examples, so yay. But we're going to be using this system to inform some other stuff. So if we have the system x prime equals x plus y squared and y prime equals negative y, then we want to first of all be able to figure out where we might have an equilibrium point or our critical points or nodes or anything like that that we were talking about from last time.
Yeah. So, try setting some stuff equal to 0. 0. We're gonna get, oh, actually. That says that x is equal to y squared, or y prime is equal to 0, says that y prime, or excuse me, y is equal to 0, and there's no undefined. So these overlap at 0, 0 only.
Mm-hmm.
Or I guess that should be minus, but same.
Yeah, I gotcha. So yeah, with the only overlap being 0, 0, this is going to be the only like equilibrium point where we have. Oh, I just did it again. Flip like, you know, the whole section over. It doesn't help. Yep, so they just come up with the fact that the variational equation for this is going to then be u prime is equal to d f at 0 of u is equal to 1, 0, 0, negative 1 times u.
Okay, I agree
I
with
was
that.
not... Okay, so can you help me out?
Sure. Yeah, so df here is taking the role of the Jacobian. So this is just a single matrix. And so that's going to be, what, y, or 1 plus 2y. Oh, nope, that's not how partial derivatives work. 1, 2y, 0, minus 1. And
Okay, there we go.
in.
Thank you. Right, that was the bit I was missing. So again, this is our Jacobian. I don't know why I couldn't see that. It's obvious when you say it like that. Right, so this is our Jacobian of system. F. Right, so then at this point, this is going to be our, it is a diagonalized matrix, and therefore we should be able to just come up with the system for this. From our earlier exploits, we probably would have said u is equal to c1, c2 like this, and then said our top one, we get x, and the x function just stays the same all the way through. U prime is equal to u through our x variable. And so this is just going to be e to the t. Mm-hmm. And then, again, we get a negative 1 on our negative 1 times u in the y position. So this should be e to the negative t. Do you want to say a however?
Nope.
Okay. I will. So because these are partial derivatives, we're not actually going to be doing C1 and C2 as constants. We're going to need constants as, oops, wait a minute. Right, okay. So the constants are specifically going to be where we have x0 for the first one and y0 for the second. So when we plug in 0 for t, right, when we plug in 0 for t, then we just end up with our x0 and y0 in those two positions. Given that, again, u of t is a variational function, it doesn't have to be exactly equal to the other one, therefore it doesn't have to exactly be going through the origin point.
So are we shortcutting here just because, so in the orange theorem we have a separate u naught. And so that's what I would have expected to show up here.
So this is u naught.
But then u naught is the same thing as x naught, then why bother?
Sorry. So this is u naught here, right? U naught is going to be x0, y0 in the system of u.
Right.
So
but that is also x of t naught, capital X of t naught.
So arg. I just entered an infinite loop. So the system for x, as in the true solution to this, should still go through 0, 0. Or at least I feel like.
Oh, right. Yeah. Okay.
And so both are x, the true solution, and y, the autonomous solution, should go through 0, 0. And here, our variational equation, u, is not going through the origin, but like reasonably close to it.
Yeah. So, yeah. I assumed these x naught, y naughts were the components of capital X naught, but they're not. The capital X naught is just 0, 0.
Okay.
Okay. I'm satisfied.
Alright, so this will essentially end up being something similar to a linearized system, and then with our nonlinear differential equations, this is like a different way of, again, looking at how to simplify the system itself. So we're not going to get a 100% accurate solution, but again, this is more for, as we said last time, for linearization. This is going to be looking at like the behaviors of the true solution that are going to be close to each of these individual points that we find.
Okay.
Alright, so I have something else that we can move on to if you're alright with. Okay with this. It doesn't have to be 100% awesome, but...
Yeah. So I guess what I'm supposed to learn, I mean, one thing that I'm supposed to learn from this is that, without looking at any pictures, I can say that there's a saddle at the origin, because the variational equation has a saddle, and the orange theorem says that okay, maybe this is not. But okay.
Oh man, where are we?
Yeah, I'll take that.
Okay, so with another system, I'm up pretty much from where we ended here.
Okay.
X prime is equal to x cubed minus a times x.
Okay.
So one of the other methods of analysis of looking at nonlinear differential equations is going to be looking at what are called bifurcation diagrams. So for this particular case, what we're looking at is what kinds of different behaviors exist for different values of a.
Sure.
And so one of the things that we can do here is say, all right, if A is going to be our independent variable, not for the system, but rather for our analysis. And X is going to be our, again, dependent variable for this analysis. It is also the dependent variable of the system, but that doesn't particularly matter in this case. What we want to do is say, okay, what values of A are going to be our transition point between multiple types of behaviors?
Okay, so the first thing that I see is I'm going to do this. And why do I want to do that? Because I think that if I'm trying to set x prime is equal to 0 to look for equilibrium points, then how many solutions I get is going to depend on whether A is positive or negative here. If it's positive, then this part has no real solutions. Or excuse me, if it's negative, that part has no real solutions. And so I'll only get an equilibrium at the origin. But otherwise, if A is 0, I'm not sure how to think about that, but also only at the origin. And then if it's actually positive, then we get 3 slowly spreading away.
Right, so in this particular case, if we have, you said A equals, sorry, 4. X prime is going to be equal to 0 if we have these 3 options, right? So you said the A determines types of solutions. Right, so A equals 0. We get our 1, 0 repeated root, whatever you want to call it. If A is less than 0, we have no real.
Well, 0 again, but not
yeah.
repeated.
Right, no real zeros for the... Oh, second, yeah. And if A is greater than 0, we have 2 extra. Equilibrium points. Right, so we're going to have Okay, so at 0 itself, we would say for negative x values, what is our x prime going to be? If a is 0, that makes it easy.
X prime?
Yep.
Is going to be x. No, cubed.
So it's going to be x cubed, which means that any negative x values as part of our solution are going to have what rate of change?
Negative.
Yeah, sorry, I'm not explaining it well. It's fine. So if we have negative x values at a equals 0, then all of those negative x values are going to have downward movement. And similarly, then, our positive x values are going to have upward movement. All right, and then the next ones we're going to be at x equals plus or minus the square root of a. So oh, right, yeah. These are going to make square root functions. So x is equal to the square root of a, and x is equal to negative square root of a. And if we pick some a value just arbitrarily, that is going to be positive, then what are the behaviors we get along this particular a value?
Okay, well, if x is really big, then everything inside is positive, so we're going to go up for the top there. And similarly down at the bottom. And if x is really small, then that middle, or excuse me, the second term is negative. And so the sign is going to be the opposite of the direction of x. So that means that we're going to have downwards in, yeah, that right there, and upwards in the other one.
Yep, alright, and usually they will draw these in with solid lines, even if I just don't want to get distracted too much there. Right, and that's going to work anywhere that we do this in the positive region. These aren't going to suddenly change anywhere. So we're still going to get any x values that are between positive and negative root a are going to be opposite the value, or opposite the sign of x. The x prime sign is going to be the opposite. And then outside we're going to get the same sign as the x value itself. Okay. And then what happens if we go over to the negative region? So if a is a negative value,
then the second term is always positive, which means it's just the same sign as x itself.
Yeah. So all of our stuff up top goes up, all of our stuff down bottom goes down. And you can kind of see, like, okay, that makes sense because, like, all of this stuff is in one region. And all of this stuff is in another region. Right, separated by x equal, or no, yeah, separated by x equals 0. And then we also have this separation here, which again partitions our system up into these two other regions, which now have opposite behaviors as the x signs. This particular one is called the pitchfork bifurcation, for, I suppose, obvious reasons. If we get rid of some of these, it's a little easier to see it. But again, the whole point here is that we're trying to create regions where we have similar similar x prime signs when we're looking at how x prime is going to be affected by the different values for a, whatever our constants are going to be. So this is also something that we do in autonomous systems. This one is also an autonomous system. It just also adds a little bit of complexity to it due to the fact that a itself is being treated as a variable here, because we don't know exactly what the value of a is going to be. Oh, that's not good. Okay, good. Discord is doing some funny things right now, so I'm going to try to ignore it. Oh no. Discord may crash. We'll see how it goes.
Alright.
Okay, so from here... we could also look at systems. And so if we look at x prime is equal to x squared plus a, and y prime is equal to negative y. So similar to but legally distinct from our previous system. Then we want to, again, take a look at this and say, what's going to happen based on the different values for a?
Right, and it looks again like there's a pretty hard separation at a is positive versus negative.
All positive and negative values?
Yes. Well, that's gonna, in the sense that that's gonna change when x prime is equal to 0. Now we could do equilibria stuff and try to figure out how that interacts with the y.
Right, so if we separate them individually and just say what's happening with x versus a,
Right.
as we did in the previous one, what are we going to get for it?
So when a is negative, then we'll have like a square root of negative a pitchfork situation without the middle. When a is positive, we get nothing. So that's going to be, everything in sight is positive, so the derivative will be positive, which means that's also what it's going to be in the upper and lower regions for above and below the parabola. That shit's negative in the middle. Yeah, x minus a is positive, but x plus a, or root a, is too small, so it's going to be negative.
Yep. And of course, again, at x equals 0, we've got this separation, which doesn't really separate anything in terms of, like, positive versus negative behavior. In this case, it's positive in both directions on the outsides, and on the positive side, it's all positive. The only exception is at x equals 0 itself. So we've essentially, we could also like show that as it starts getting closer to 0, like the amount that it's changing is a lot smaller than the ones that are going to be out here. And do like a weather map or something. Right, as we start getting away from x equals 0, we start getting stronger and stronger motions for x prime, which really isn't that surprising. Okay. So then this is going to produce actually different results for our overall phase plane, which is x versus y. Or y versus x. Right, so this is a bifurcation diagram at the top right. For x versus a, whereas our phase plane is y versus x, given a particular a. So we'd have to choose, like, which version of a do we want to use here, and then from there discuss what's happening with the phase plane.
Sure.
So in this case, let's do less than 0 over here. A equals 0 here. And a is greater than 0 over here. So again, what kinds of behaviors are we seeing? For the kids at home, which one's the easiest one?
Probably the positive.
Right, I tend to agree. So fewest changes of all sorts of weird stuff. So we're going to say with a... Oops. Just pop that over the top of that thing. With a being greater than 0. Hey, Plasma. Yeah, thanks. The family moved out here about 4 months ago, so we're, you know, getting settled in. We just did a plan this week. We said we're gonna ride our bikes to the nearby town, which has like a very beautiful greenway, which goes from one town to the other through like bike safe and walking safe paths. It's very nice. So we went about it's about 5 miles away to the town. We went 2 miles, give or take, on our first day, 2.5, somewhere in there. And so our round trip was pretty close to 5 miles. And I was like, okay, I'm feeling pretty good about this. Let's go a little bit further. So yesterday we went and we ended up doing a 7 mile round trip. I was like, okay, let's see how we're doing. So we woke up this morning and like none of us were particularly sore. So I'm like, all right, let's just see how it goes. We got to where we stopped yesterday when I was like, maybe we ought to turn around, and everybody's like, yeah, I'm feeling kind of tired. We got to the same place today and they were just like, let's keep going. I'm like, all right. So we made it all the way out to the next town over, 5 miles away. And as a reward, we stopped in for lunch and then stopped at their world famous ice cream parlor.
Oh.
And then rode all 5 miles back, and nobody complained, so we're doing all right.
That's pretty good.
So I was like, oh man, I am really proud of you two. They are 8 and 11, so I mean, it's not like it's a small feat, especially for the 8-year-old.
Yeah.
But I went down there by myself, months ago when they were in school. And I was like, this is a nice ride. So today was also the first day that I rode them entirely on the roads to get there, rather than like hopping off and walking for a bit, especially in a couple of the roundabouts. Today I was like, we're just going the whole way, follow the traffic signals. You know how to do your the traffic signals with your hands and things like that. So today was the first day that I took them out on the road for the whole day, or for the whole before and after trip. So it worked beautifully. Everybody, I think, is staying safe, so we'll just get some more practice on road riding. But yeah, these two have been like riding around our parking lot that we live on, our little cul-de-sac, whatever, for miles at a time. It's just that they're right outside, so I don't actually notice how far they go. All right, anyway. So if we're looking at the case where a is greater than 0, what are we going to get?
Well, at y is equal to 0, that horizontal line, everything is pointing left, right. And then as you go up, it starts to point a little down. As you go down, it starts to point a little up.
Yep. So over here we get some mild, right, downward pointing stuff. And then up here we're going to get much more pointed downward stuff. So essentially, right, we're going to end up with stuff that looks like this. Also, actually, other important point. There's something else that's important.
I don't know.
So we'd said from the bifurcation diagram that when x is equal to 0, we have no horizontal movement. So
Right.
that's going to be important. I completely forgot about it. So as this stuff moves down, it's also going to get closer and closer to 0, where...
Wait, no, that's not true. When x is 0, we have movement, we have a.
Right. Oh, yes. And this is a is greater than 0.
Yeah.
Yes. Okay. Thank you. Sorry.
All good.
Forgot which one I was on. Right. So whatever a is, that's going to be our predominant movement as we go through. Okay. Thank you. Alright, same stuff up here. And then we're going to have continuous right movement along the y-axis as well. Okay. And if we want to know exactly how all of these phase planes look, naturally we can just take this stuff, plug it into our phase plane program that I had on GeoGebra. Okay, now if we move to a equals 0...
Yeah, on the horizontal line, we still have everything pointing to the right, but those pointings get smaller close to the origin, where there's no movement.
Right. So this is where we start getting everything dipping down towards 0. And eventually, as we get close to our origin point, all this stuff starts slowing down eventually. Essentially stopping right at it. This also means that the stuff that is directly above and directly below are going to be pointed directly toward the origin as well. And then coming away from the axis, over into the positive region, we still have stuff that's going to fall toward y equals 0, but it's going to look a lot more like the stuff in the a is greater than 0 section. This is going to look essentially like exponential functions. Okay, so it is important for us to note that, right, at 0, 0. This isn't going to be a hole, it's just going to be a sink. So we're going to have a sink point. And also because it has the same behavior on both sides of x, this is also going to be classified as semi-stable. So we talked last time about semi-stable, stable equilibrium points and unstable equilibrium points. This one is semi-stable because if we're coming at it from the negative side, everything is going to go toward it. And if we're going from the positive side, everything is going to be moving, at least horizontally, away from the origin point. All right, and what about if a is less than 0?
Well, there's, I guess, going to be 3 or 2 vertical lines at x equals plus minus square root of a. At both of those points, do we have direct downward movement? Or movement toward the origin, or the axis? We're going to have no x.
Right, negative square root negative a and positive square root negative a.
True.
Okay.
X prime is 0, and so y prime is negative y. So yeah, we're going to have this sort of this picture, but copied over on those lines.
Yeah. So we're still going to have movement toward our x-axis. The next question is, what happens with stuff that is around it otherwise?
So let's be positive x and move a little bit left of the line, then that's going to be a negative x prime.
Yep, so all the stuff in between those two vertical lines is going to be moving toward the negative side,
the origin,
as we saw over here, right?
Yeah,
both of them are going to be moving toward the negative side. So we're going to have stuff that's going this way, and stuff that's going to be moving this way and this way. And based on our y's, again, the further away you are from the x-axis, the larger the change is going to be. So we're going to have something much steeper up top like this. All right, let's do far negative.
Far negative. Then x prime is positive, so we're going toward the line.
Right, so positive direction.
Mm-hmm.
And again,
But,
our y's do the same
negative,
thing.
So yeah.
Yep. Small when we're down low, big when we're up high. And same thing down here. And far positive.
Again, we have x prime is positive, so these are going to be copy paste the picture on the far right, left.
Right, so all of our stuff over here ends up doing something like, doing something like this. All these are going to the right. All these are going to the left. These are going to the right again. Realistically, right, we could take this line here and copy paste it as our x-axis.
Right.
Okay, and then this one's going to be like that. Gonna be like that. So what kinds of locally linear systems do we have in each of these locations? quote-unquote most important locations.
Looks like we've got a saddle at the positive, the sink at the negative.
And I can't draw, but whatever, it's fine. Yeah. So again, here,
it's surprising to me that we would describe that as semi-stable. Like, because this is like almost unstable, right?
It is, right? Like a nudge in literally any direction except the vertical will push it onto an unstable path. It'll move it somewhere completely different. But if you nudge it exactly in the vertical direction, then it will return to its current position. So it's a technicality, really. but it is still considered semi-stable. It doesn't have to be literally half of the outcomes. And here, yes, stable sink. And for a is greater than 0, we had no individual critical points. I believe that was the case, yeah?
Right.
And therefore no equilibria to speak of. All right. Thoughts on this?
Is it useful in your experience to think about... So here we're assuming that A is constant. But it doesn't seem to me, if A were allowed to change very slowly, that there would be like a qualitative change in these pictures until you got like close to these bifurcations. Is this like a sort of analysis that gets used to think about non-homogeneous systems?
If we want to get super technical about it, it already is a non-homogeneous system as long as A is not 0.
I suppose. Yeah.
But yes, I understand your point. Yes, I think it would be a first step, would be to say, okay, if A is constant, this is what we're going to do. And we get these bifurcation diagrams. If A is non-constant, so if A is time variant, then we would want to know when A reaches each of these different states. And then how would it change from one to the next to the next.
Okay.
So I've never actually done like any serious analysis or like research in nonlinear differential equations. I did do a like project or 2 or 3 projects in nonlinear differential equations, but again, that was 15 years ago and haven't touched it since. But yeah, the first step would be, what if A were constant? let's show the bifurcation diagram, and then if it's not constant, how do we get to these states? Absolutely. Right, because this is also, like, you can create a continuous video to get from one to the next to the next.
Right.
For all these.
Right. Okay. Sorry. I had to work to get the negative side, but yeah, I see it.
Although, right, going from a equals 0 to a is greater than 0. If it's even
is also interesting.
1/1,000,000th,
yeah.
right? It's just gonna jump, like it's just gonna fly out to infinity.
Yeah.
So maybe not technically continuous, but okay.
Yeah, and what happens if we linearize at a equals 0? Because that local picture doesn't look like anything we've seen so far.
Right, so if we linearize, that is doing the Jacobian
Right.
at the point where we have, this would be x squared. So we're going to get 2x,
Gosh.
0. And then 0, negative 1.
Minus 1. Ah, because we have a 0 row. That's why it doesn't look like anything we've done before.
Yeah. Right, so if we do at 0, 0. 0, 0, 0, negative 1. So not particularly helpful in that sense. So we would essentially just have x as a constant and y is equal to e to the negative t. Alrighty.
Okay.
Alright, so if we I want to explore a couple of application examples. They're not necessarily going to be things that we can like delve humongously into, but just things to think about if anyone is interested in looking at different kinds of models. One that happened to be very relevant somewhat recently is what's known as the SIR model. Which specifically looks at the infection rates or the spread of infectious diseases. S is going to be the number of susceptible individuals within a population. Infected is I, and recovered is R. Recovered does, in fact, include those who have passed away from this particular disease that we're talking about, because they're unable to pass on, once they're unable to pass on the disease, they technically join the R queue. As odd as that might be. The overall equation for this, again, it's likely that people have seen this. There is going to be a rate of... This is the number of... right. S prime is going to have the non-zombie model. Yes. Thank you, Aperiodic. Negative B is going to be essentially the transmission rate of a particular disease, and then you're multiplying by S, the number of susceptible people in the population at present, times the number of infected people at present. So this gives like the transmission rate given all of the measures that are being taken to try and lower the transmission rate. It also includes just the natural transmission rate of the disease itself. It is talking mostly about like what are the chances for transmission based on interactions between these two populations. All right, plus the number of susceptible people is also going to be increased by a retransmission rate to the recovered people. So recovered people may re-enter the susceptible population with a rate of mu. Creepy music again. I prime is going to have the exact opposite term, beta Si, because all of the infected people are going to be, again, taken from susceptible to infected at that particular rate. Again, transmission rate, minus nu I, which is going to be the rate at which people will recover. However we're terming recover at this point. Recovered population then increases by that particular amount, right? Nu times I. And then loses people based on the mu R, which again, we can kind of asterisk this and say, okay, but also there is the possibility that if there is a lethal infection, then we're going to, end up losing people entirely from the system. It's possible, so you just have to watch your numbers and plan accordingly. In this particular model, they're just saying that this is a closed system, that we're not going to lose people from the total overall S plus I plus R. So it is a bit of a simplified model, but yep. S plus I plus R prime is going to be equal to 0. So total number of people will always stay constant for this particular thing. So this particular nonlinear system is, fairly complex and obviously does not reflect 100% of reality. But again, it's a reasonable assumption that as long as the fatality rate is not hugely significant, if it's something like the common cold, right, we can approximate it using this. Stuki, do you want to add anything or questions or anything?
No, I'm good here.
All right. There is also the... This is the... infectious disease. Okay, there is also the predator-prey. Unfortunately, both of them start with P, so we're going to have to delineate it a slightly different way. I'm going to go with carnivore and herbivore. Oversimplification, but whatever, it's fine. Typically, we have something that ends up being like an A times C is going to be the natural growth rate of the carnivore population. Is that backwards? That might be backwards. Minus bxy, yeah, that's backwards. Okay, so our A value is going to be sort of the natural exponential growth rate of our herbivorous population, and this allows for unbounded growth, so we're talking about a small area and this group can spread out from there. All right, minus, and this is our interaction term, so B times C times H is going to be the number of interactions that occur. Every interaction that occurs between carnivores and herbivores ends up with an herbivore dying in this particular model. Again, or occurring with a certain rate B. So our carnivorous population will also just, if left alone to their own devices, is going to not survive. So the only way that the carnivores can continue to survive is if they have continued interaction with the herbivorous population. So we're assuming that they are carnivores. They only get their food from predating these particular herbivores. So without any herbivores in the population, the carnivores will have an exponential decay in their population. So oftentimes this is going to be given as right, H times the quantity, A minus B times C. And our carnivorous one is going to be given by C times the quantity, negative C plus DH. And if anybody knows the kind of functions that each of them individually are expressing here, more or less. It's not fair because it's in two variables, so it's not a 100% fair question, but if it were only in one variable, we have our growth rate is determined by the current population times another term which has that same population in it.
Right, so that's sort of an exponential growth decay model.
So it incorporates both. Right, our H prime is going to be directly proportional to both the current population and the interactions with the other population.
Right.
And again, if it was just like itself, if it was just in one variable, what population or what function type would that be with both of those terms in there?
Oh, that's like logistic.
Yeah. So in this case, it's logistic, and to make matters worse, it's interacting with each other. So the top population limit is going to be based on their interactions with each other. I also worked with, for one of my projects in nonlinear differential equations, I added a third, which was a scavenger species. So what would happen if the predators, the prey, and the scavengers all existed within a certain area? So I did some modeling with saying that the scavenger species if left alone, again, they would end up having a negative effect on themselves. But then they also have a positive effect on the interactions between both species. And also, there would be some effect with what would happen if each individual species were just left alone by themselves and had a negative growth rate. So I don't remember how I did it, but I don't remember exactly how I did it, but I added a term that meant that if it ends up with a negative growth of the other species, then it ends up growing the scavenger species. So I played around with this a bit and ended up creating a pseudo neural network. It wasn't a literal neural network, but it was one of the strategies that John von Neumann's one of his colleagues created, called a Cahonin map. So I found some code for a Cahonin self-organizing map, and I ended up altering it to do this predator-prey-scavenger model, which I found rather interesting. I just basically played with parameters until I got something interesting, and then showed all of my results to my class. Teacher and the other students in there really loved it, so I might be able to find it again.
That would be I'd love to see that on stream sometime. Yeah.
Yeah, I think I might have done it like during one of my first few dozen math nights, but you know that was like 2 years ago. Baby Obi. Let's see. It probably also did not 100% reflect reality. I think it also basically like took a sample of the areas and then like plotted one particular point, found its relationship between the three species, and then did a like exponential decaying change. So it said like, you know, this point is now going to be, if, you know, pure herbivores or whatever, and then it's going to radiate outward and drop off. And so it probably isn't what I meant it 100% to be originally, but you know, it was still an interesting project overall. And to try to bring in some of the neural network stuff, the other, I think my professor was interested in seeing that connection most. And what's this? Why is that page folded? Oh, that was just old homework. Alright, so one of the other famous nonlinear differential equations problems is going to be the two-body problem, which then expands to the three-body problem. We're not going to be just explaining the whole thing, but in the two-body problem, Newton's law of gravitation is going to tell us that we get m1x1 double prime. So in this case, we're looking at the F equals ma formula, right? The forces of gravity on both sides are going to be equal on both sides. So mass of the first times its acceleration has to be equal to our GMM, M1, M2, over, and in this case it is, normally it would be just the distance of these things squared. However, it is, the issue is that if we square it, it's always going to be positive. So in this particular case, they did actually want to preserve the sign of the interactions that are going on. So they said, okay, let's take the distance between these two things, and instead of just squaring it, we're going to take the absolute value of the cube of this thing and then take off one of them, x2 minus x1, which will also then alter the sign. And then similarly for M2x2 double prime. C2 G G M1 M2 all over absolute value x1 minus x2 cubed divided by x1 minus x2. And again, same deal here, just other way around. So in doing this, it creates a nonlinear system of equations, which ends up with a lot of terms which potentially get a little confusing. But with a two-body problem, this is solvable. It's just going to be kind of rough to get through all of it in general. So with three-body, I think you can probably see where this is going. We're going to have something with m1 x1 double prime, m2 x2 double prime, m3 x3 double prime, but now this has to include on the right hand side, you know, our g m1 m2 and a term for g m1 m3, and similarly for the others. So with all of this, now we've got a yeah, we have an order 2 differential equation first of all. We have not talked about second order differential equations, but that's fine. Again, we're not trying to solve it at this point. We're just highlighting the issues that come about. And in this particular case, right, we end up with these massive systems that are all dependent upon each other. So we're going to have in our first equation stuff with all x1, x2, and x3 in them, just in different terms. And because these are not separable, because these are not movable into any useful state, we're just not going to be able to solve it. So the three-body problem ended up becoming a huge issue for Newton, like instantaneously. As soon as he tried to calculate even the simple version of the Earth, the Moon, and the Sun, it was just impossible to figure out. And never mind the fact that, like, you know, all of the bodies in our solar system are pulling on all of the other bodies in the solar system. So this becomes an effectively exponentially growing issue as you start including more and more individual astral bodies. I shouldn't say astral, but it's true. So, three-body problem ends up becoming completely unsolvable. I suspect that if it were to be even possible to solve this, we would have to have somebody invent mathematics on the genius level of Newton. So, like, the jump that occurred from pre-Newton-Leibniz to post-Newton-Leibniz, we would need that all over again. And I don't find it necessarily likely that there is even a way to manage this. And, I mean, we're talking like Einstein worked with tensor calculus very casually. He was able to, you know, come up with huge amounts of solutions to differential equations using tensor calc. And yeah, this is not doable. Anything you want to add about that one, Stuki?
I don't think so.
Okay. I can also let you go if you're...
Yeah, I should head off.
Okay. So we're just going to discuss the last chaotic systems, and yeah, I'll just put up the equations for those. So if anybody out there, Stuki and Zach, or anybody else in the community wants to work with it, I'm going to post those here and then put them on Discord, and feel free to check them out. Feel free to do some modeling. It's really cool stuff. All right. Anything you want to plug?
Nothing in particular. I'll probably be back to stream on Friday, but who knows?
Woo. All right. We'll see you Friday.
Take care.
Bye, Stuki.
Bye.
Okay, so I found the simplified versions of the chaotic systems that we were talking about last class. I briefly discussed them, but I didn't actually write equations out, because I knew that I had them somewhere. It's just that I could not find it before last class. Sorry. So here, the Lorentz system, this was our... what I'd talked about as the Lorentz attractor. Doesn't really, well, whatever. It's fine. Basically, looks like, well, it's the thing on the cover here of this particular book, Dynamical Systems. These are just really awesome. Merriweather, yeah, just completely unsolvable. The number of terms that need to be added for every new body that you add ends up increasing the system by just that much more. If we were to add a fourth body in here, right? Let's look at that real quick. I'm not going to write it out, but if we want to add a fourth body in here, then that ends up being, we need G 4, 3, and 2, or sorry, 4, 3, 4, 2, and 4, 1. So it's going to add an entire, both row and column to this. So that ends up making it increased by a square factor every time that it goes up. So from 2, right, a 2-body system requires 2 terms and 2 equations. A 3-body system requires a 3 by 3, so that's 9. A 4-body system requires a 4 by 4 in order to express all the individual terms. So that's 16. Again, it's just going to keep increasing by the square. Or we're going to increase by a constant every time, but it the amount it's increasing is linear, but the number of interactions that exist are squared from the number of bodies that you're talking about. So it's just keeps going up like a parabola. Do the scientists just guess? No. So good news. You don't just guess things. You take current observations and you plug them all into a system, and then you say, okay, based on this stuff that we had here, we're going to get parameters. Those parameters are the following. So you plug in like all the G variables that you got, all your masses that you've got, all of the positions that you've got for all of these particular values in the past. You then plug them all in to make sure that all of the parameters are correct. And then you say, okay, tick forward some number of time steps. And so it does essentially our like Runge-Kutta calculations that we did for differential equations way back at the beginning, when we said, oh, we need to take the sum of these things and then affect them, and again, essentially doing Simpson's method on these constants in order to create the new value that we've got. And it does really well. The system as a whole can do Runge-Kutta and stays pretty accurate. But I think you know that we have not figured out how to predict the weather yet. which is the same problem with even the 3-body problem, is that what happens is you keep ticking forward those little time steps, and even the most accurate system that's out to, like, you know, accurate to 24 decimal places or something like that will eventually start breaking down and start producing one result if you have a certain set of parameters, or if it slightly rounds differently, it can go in a very close but not quite the same path. And if those two things end up continuing, they will diverge from each other radically. So you'll notice that there were 2 Lorentz attractors on this page. The one on the top has an initial value, which, actually I should show the one that's in the book, has the initial value P1, and the other one has initial value P2. You can see where those are down at the bottom here. And they're, like, reasonably close to each other. It said the initial conditions P1 was 0, 2, 0, and P2 was 0, negative 2, 0. So compared to the other values that are on this particular attractor, they're, again, reasonably close. But the problem is that P1 ends up going this way, and P2 ends up going this way. Like, they start moving in different directions. They don't even, like, end up in different directions. They start moving in different directions. So it's pretty wild. The amount of, like, the amount of change that exists between things that have ever so slightly different initial values is what is going to cause the, and this is the literal correct word for this, the chaos that exists in this system. So here we have x prime is equal to sigma times y minus x. Y prime is equal to Rx minus y minus xz. Z prime is equal to xy minus bz. So the stuff that I was talking about with Runge Kutta and stuff like that, those are numerical methods, which are the introduction to ODEs. And the whole class that I'm doing here is ordinary differential equations. It's introduction to ODEs, that sort of stuff. The stuff that we did tonight was nonlinear ordinary differential equations, but these are going to be much more advanced topics than you'd find in a typical ODE class. I just wanted to touch on stuff tonight to kind of get a feel for what's out there and, like, what kind of cool stuff we have. I also wanted to discuss a couple of linearization techniques with Stucky, and that included some stuff that I was stuck on when I was trying to review all of this. So, thank you, Stucky, for putting up with me tonight. Alright, let's see. That's a particular model. Yeah, here we go. This is the... Was I trying to get to the other one? There was also a thing in here on, like, the rules for attractors, and that was kind of cool. Because attractors can't just... There we go. Attractors just can't, like, be created by throwing random stuff at the wall and seeing what's going to happen. These were developed by, obviously, Lorentz, multiple mathematicians who were looking into particular types of nonlinear differential equations and their consequences, and ended up like stumbling across these particular behaviors that they were like, that's a little strange. Let me try changing something just a little bit and seeing what happens. And when they did, they got these things, which the Lorentz system is like almost stable, right? It stays within a certain distance of the origin. And there is actually a limit to it where you could actually plug in numbers and figure out what like the maximum value you could possibly get is if you start within a reasonably small area. I don't know how to do it, but there is at the very least a way to figure out what the maximum value is going to be. I think it has something to do with like effectively figuring out the kinetic energy of the system and being like, you know, if we have this much energy to play with, how far can that energy get pushed? So I want to define attractors just generally. Everybody's going to be bored the hell by this, but nonetheless. So what we were talking about earlier was our system was being run through this particular function. And in this case with the Lorentz system, right? Our function is going to take each of these parts and then start saying, okay, we're going to take negative sigma times x plus a sigma times y. And that's going to get us our first term in x prime. And then in y prime, we take r times x and negative 1 times y and x times z. We subtract x times z. Right, and then we do the same thing with z prime for the following stuff. So our function is going to operate on our x vector, which in this case is x, y, z. I know that might be a little weird, confusing, whatever. It's fine. This is going to have a flow, which is also going to be defined as phi sub t. Flow is further defined in here, and I'm not going to go into it because I don't entirely understand the whole thing, and I didn't really have time to like sit down and actually look at it for hours. So a set of points, which then a set of functions, a set of yes, points. A set of individual points, which is going to be lambda, which belongs to our, you know, real nth dimensional system, is an attractor. If the following are true. So there are particular rules that have to be followed if you want to know whether something is an attractor. So 1, lambda is compact, and I think probably this is going to be best understood through Penn Center's complex analysis class. Like, I don't remember 100% what compact means. If anybody in chat knows, feel free. and time invariant. So this is a concept, time invariance is a concept that Stuckey and I had discussed before, where we're saying it doesn't matter when you hit that point, but if you hit that point, the behavior from that point is always going to be the same. So the behavior at any given point is deterministic, and it doesn't matter when you hit that point. Time invariant. All right, 2, there exists an open set U containing lambda, come on, stop, such that for all t greater than or equal to 0, and to me this looks like intersection, t greater than or equal to 0 combined with the flow. No, that's got to be a matrix. That's weird. Anyway, times the flow of t at u is going to be equal to lambda. So whatever this matrix is, we're multiplying it by our flow matrix, and we're getting all of our individual points lambda. Okay, and also transitivity has to exist. Which in this particular case is given points y1, y2, which belong to lambda, and any open neighborhood u sub j about any of those points y sub j belonging to u there is a solution. Curve that begins in u sub j. Nope, u sub 1. And later passes through u sub 2. Alright, so given any points y1, y2 that are in lambda, And then we have any open neighborhoods that exist about those 2 points. There must be a solution curve that begins within the neighborhood of U1 and later passes through the neighborhood of U2. So this is also kind of interesting if we look at it from the perspective of like some sort of attractor, right? Y1, Y2. Sure, why not? Right? So we start at any particular point. We have to end at another point which is in the other neighborhood if this is truly an attractor. So all neighborhoods surrounding Y1, no matter how big they are, no matter how small they are, if we have an attractor, then we can start somewhere within a neighborhood around Y1, and we must eventually get to within the other neighborhood around Y2. That's what this is saying. And they're open neighborhoods, so you can't land on the perimeter of it. You have to land somewhere in the middle. I believe those may have to end up being the same size, but it may also not. So no matter what size of the neighborhoods you use, you may actually be able to say that, you know, eventually we must end up within any neighborhood. Yes, any open neighborhoods U sub j about y sub j. So I want to pick a U sub 1 that ends up being like that small, then this must exist if it truly is an attractor. Alright, that one's going to be like really big, so it could be anywhere. Right, so eventually it must end up within the other neighborhood at some point. It may take a very, very long time to land within a neighborhood that is this big, but nonetheless, all points that are within the system lambda, you can pick any size neighborhood you want, and if it is truly an attractor, it will end up landing within that neighborhood, given that you started within one of the other neighborhoods around another point. Whew. Alright, and then I want to do just the Rössler attractor, because this one's also kind of fun. X prime is equal to negative y minus z. Y prime is going to be equal to x plus a y. Z prime is equal to b plus z times x minus c. Alright, again, here we have an interaction between z and x. Z prime ends up being large, and then if x and or z are going to grow, then we get that, but also just z by itself is going to cause z prime to drop. So if the x value is greater than the c value, we're going to end up with an overall net positive on z, and it becomes essentially exponential growth. Okay, so this is an interesting one because there's a lot of feedback which goes into it. So you notice here, right, this is going to be, if a is positive, this is going to be exponential growth again. But as y increases exponentially, it's going to also cause x prime to decrease and eventually become negative, which means that this is going to become negative, and it can grow possibly even more than exponentially. I'm not sure exactly. This one says they have they picked a value of a as a quarter, b as 1, and c anywhere from 0 to 7 to see what would happen. So that's pretty fun. It's again with stuff like this. I think it's something like that. No, the big ones get small. Okay. It's really weird. So the ones that go really big end up having like a really small hump here, and then end up going inward further. It goes like that, and then hops like way out to the outside. Something like that. I don't know. It, I guess, kind of looks like a chair a little bit, like the palm of your hand held up like that. Anyway, that's another fun one to take a look at if anybody is interested in doing a little bit of research on some of the attractors that exist and other nonlinear cool stuff. So next week, what we're going to be looking at is how to take first-order systems and turn them into second-order differential equations. Then, how do we deal with second-order differential equations? Because, oh no, that's completely different, right? Right? Maybe not in as many ways as we would like to think. So, I would like to head on over to somebody. The only person who is literally in the same category is currently speaking Russian, so we can head on over to see Balint at Science Streams. Hey, thanks, Aperiodic. No worries. So Balint has about 7.5 more minutes or so until he will be in. Today is Art Wednesday. Balint and his wife Lita are biologists, anyway, who have spent their lives working on ants and trying to understand ant behavior and all sorts of really cool stuff. So, we're going to head on over there. Again, today he's working on art, which is usually like changing up some of his emotes or something like that. Typically they are ant focused. So let Balint know when we're when he's on that you came from here, and we'll have a good time. I will be back on Friday for gamey type stuff, and next week both Monday and Wednesday for differential equations, and Tuesday maybe we'll do some more like math help, math questions stuff. I wasn't in yesterday because I had to deal with some weird things that were going on with our insurance. So, yay! I'll see you all later. Good luck. Have a good rest of your week. My name is Obi-Wan Pez, and this is N Simplex Pachinko. Have a good night.